Welcome, everyone. I am so thrilled you're here today. We're diving into a very special explainer where we're going to take Andrew Ng's legendary Stanford Computer Science 229 lecture and basically translate it into a foundational map of machine learning. So if you're a focused learner looking to systematically wrap your head around this massive technological landscape, well, you're in the exact right place. We're going to build a highly structured, highly visual toolkit together.
Andrew Ng famously stated that AI is the new electricity. Honestly, this is such a profoundly powerful way to frame the source material. I mean, think about it. Just as the emergence of electricity transformed absolutely every major industry 100 years ago, artificial intelligence, or what engineers often more specifically call machine learning, is poised to do the exact same thing right now. The stakes for understanding this technology literally couldn't be higher.
Okay, let's dive into our map for today. First, AI is the new electricity. 2, what is machine learning? 3, supervised learning. 4, unsupervised learning. 5, reinforcement learning. And finally, 6, machine learning strategy.
Jumping right into Section 1, AI is the new electricity. You know, the demand for machine learning skills right now is just staggering. The real-world opportunities are vastly outgrowing the number of people actually trained to do the work. And it's no longer just some shiny toy for elite tech companies either. Right now, we have English professors applying learning algorithms to understand history, lawyers completely automating the processing of complex legal documents, and there are massive, game-changing transformations waiting to happen in healthcare, manufacturing, and logistics. It's a real opportunity to build incredibly meaningful applications across literally every imaginable industry.
Which brings us to Section 2. What actually is machine learning?
To really define this technology, historically, we have to look at Arthur Samuel's classic definition. He called it the field of study that gives computers the ability to learn without being explicitly programmed. The story behind this is absolutely fascinating. So decades ago, Samuel wrote a checkers playing program. And back then, people were deeply debating whether a computer could ever do something it wasn't explicitly coded, step by step to do. But by having the program play tens of thousands of games against itself, it learned the board patterns that led to wins and losses. And eventually, the program actually learned to beat Arthur Samuel, its own creator.
Now, compare that older kind of magical concept with Tom Mitchell's modern well-posed definition. He states that a program learns from experience E with respect to some task T and some performance measure P if its performance improves over time. Let's ground this. In our checkers example, the experience, the E, is those thousands of hours of self-play. The task T is the actual game of checkers itself, and the performance measure P is the statistical chance of winning against the next opponent. It's just an incredibly clear mathematical way to frame exactly how algorithms learn.
Moving on to Section 3, Supervised Learning, Guided Predictions.
So supervised learning is where you give the algorithm both the inputs and the correct answers, so it can learn to map them together. This is by far the most widely used branch of machine learning today. Now, what's really interesting here is how we map these inputs to outputs, because we're either predicting continuous data or discrete data. Regression is for continuous outputs, like, say, plotting a line through a graph to estimate housing prices in Palo Alto based on square footage. You're predicting a number on a sliding scale. Classification, on the other hand, is for discrete data. Think of a medical diagnosis trying to predict if a breast tumor is benign or malignant. It's essentially predicting a 0 or a 1, just sorting data into distinct categories.
But of course, real-world problems are rarely just two-dimensional. In actual medical applications, you would use way more features than just tumor size and a patient's age. You'd be looking at cell uniformity, clump thickness, adhesion, and dozens of other metrics. What's completely mind-blowing from the source material is that brilliant algorithms like support vector machines can actually compute using infinitely long lists of features. Through a clever mathematical technique called kernels, the algorithm can handle an infinite dimensional vector without running out of computer memory. It's pretty amazing.
And supervised learning is also exactly how early autonomous driving worked. Think back to Dee Pomerleau's autonomous vehicle at Carnegie Mellon. The process was surprisingly straightforward. Step 1, they digitized the front-facing camera image. Step 2, they continuously record the human driver's steering direction as the correct label or answer. And Step 3, they run it through an artificial neural network. The algorithm simply learned to mimic the human driver's steering output based entirely on the visual inputs it was receiving.
All right, let's jump to Section 4, Unsupervised Learning, Finding Patterns.
With unsupervised learning, we don't give the algorithm any labels or correct answers. We just hand it a bunch of raw data and basically ask it to find interesting structures all on its own. Consider this deeply engaging challenge, the cocktail party problem. Imagine a super noisy room with overlapping voices and multiple microphones picking up all the audio at once. How do you separate the audio so you can hear just one person clearly? Because we don't have pre-labeled isolated audio tracks to train the system with, supervised learning simply won't work here. Instead, we use an unsupervised learning algorithm called independent components analysis. It analyzes the raw, chaotic data and mathematically separates the overlapping voices entirely on its own.
These unsupervised algorithms, particularly clustering algorithms, are working behind the scenes everywhere you look. They're what Google News uses to group related stories from thousands of different news outlets into one unified topic. They're used in computational biology to understand complex genetic microarray data and group individuals with similar traits. They're exactly how platforms find cohesive communities in vast social networks, and how businesses segment users for highly targeted market research. You give the system chaos, and it finds the categories.
Next up, Section 5, Reinforcement Learning, Earning Rewards. This brings us to the bleeding edge of robotics and game-playing algorithms, and this brilliantly illustrates a key question. How do you actually write a program to fly a Stanford autonomous helicopter? Well, the truth is, you can't. Humans actually do not know the optimal mathematical way to move the control sticks to execute complex maneuvers like flying upside down.
So, if we don't know how to do it, how do we teach a computer to do it? Andrew Ng uses a hilarious and honestly perfect analogy here. Good dog, bad dog. You essentially just let the algorithm try things. When the helicopter flies accurately or executes a maneuver well, you send a positive reward signal. Good dog. When it crashes or drifts off course, you send a negative reward. Bad dog. Over time, the algorithm learns to maximize those good signals and minimize the bad ones, effectively teaching itself how to execute incredibly complex tasks.
And that takes us to our final section, Section 6, Machine Learning Strategy.
Look, knowing all of these brilliant algorithms is entirely useless if you don't know how to deploy them efficiently in the real world. In the past, debugging and improving learning algorithms was treated almost like black magic, or tribal knowledge. Teams would just waste 6 solid months blindly tuning data, tweaking parameters, and basically just hoping for a better result. Today, we absolutely have to treat this as systematic engineering. By using a structured strategy, you can quickly profile your algorithms, figure out if you actually need more data or just a different model entirely, and save your team from wasting months on completely unpromising directions.
And that brings us to our ultimate question for today. We've mapped out the toolkit. We've seen exactly how supervised, unsupervised, and reinforcement learning work. We've learned that you must deploy these strategically. So, how will you apply this new electricity to ethically remake your own industry? The demand for this knowledge is absolutely massive. The tools are increasingly clear, and the real meaning of this technology lies in the incredible things you choose to build with it. Thanks so much for joining me on this explainer, and I really hope this leaves you inspired and ready to plug into the future.